I'm cool with the 96 though.
Okay, so today we do 6.2. So we go back and we cover one-to-one functions. And the reason we cover one-to-one functions is because one-to-one functions have an inverse function. So we refresh on one-to-ones and inverses, which will lead us into 8.1 and 8.2, which is all about inverse trig functions. So we're going to learn how to create an inverse trig function. But again, today, we just refresh on what a one-to-one function is and an inverse. So remember, to be a one-to-one function, the inputs in the domain must correspond to two different outputs in the range. So that means x1 and x2 are two different inputs of a function. So to be one-to-one, every x value has one and only one y value. So if we look at that my little blobs below, the first picture represents a one-to-one function. Every x has its own y value. So every x has one and only one y value. Now, the second picture is not a one-to-one function, but it is a function. So x1 goes to y1, x2 goes to y1, and x3 goes to y3. It is okay if multiple x values share the same y value. That's a function, but it's not a one-to-one function. To be one-to-one, every x must have exactly one y. They cannot repeat. And the third picture is not a function at all, because now one x value goes to two y values. All right, but again, our focus is on a one-to-one function. Every x must have one and only one y. Okay. So for the first example, we are just given a set of coordinates, and we want to know, are they one-to-one functions? For the first set, -2, 6, -1, 3, 0, 2, 1, 5, and 2, 8. Is this a one-to-one function?
Yes.
I say it is.
Yes, good, because you do not see any y values or x values repeated. So it is a one-to-one function. So good. All right, the second set of coordinates, 2, 6, -3, 6, 4, 9, 1, 10. One-to-one or not?
No.
No.
No. Good. Because 2 goes to 6 and -3 goes to 6. So this means that they do not share, or they do not have one and only one y value. Whoops. What did I hit? Go back. There we go. All right. So no. Okay. So another way to check if we have a one-to-one function is using something called the horizontal line test. This means we would be given a graph of the function, and all we would have to do is draw a horizontal line through it. If that horizontal line only intersects the graph once, then it is a one-to-one function. So let's look at the graph of x squared. We know what x squared looks like. So x squared looks something like that. If I were to draw a horizontal line through it, how many times do I intersect it?
Twice.
Twice, which means x squared is not one-to-one. Okay, and then we can look at the graph of x cubed, which looks something like that. If I were to draw a horizontal line through it anywhere, you would only intersect it how many times?
Once.
Once, which means x cubed is 1-to-1. Perfect. Also a nice little theorem, a function that is increasing on some interval is a one-to-one function, and a function that is decreasing on an interval is also a one-to-one function. So x cubed is an all increasing function, meaning that it's a one-to-one function. Okay, and the same could be said for an all decreasing function. X squared is a decreasing and increasing function, therefore not one-to-one. Okay, any questions on that first page?
Nope.
No. Good, good. All right. So now we'll get into the definition of the inverse. So suppose that a function is one-to-one. This means that each x in the domain, there is exactly one y in the range. So if we were to look at these blobs down below, let's say that here's my x, here's my y. And to go from x to y, we would use the function f. So to get from the domain of f to the range of f, from one x value to exactly one y value, we would use function f. And this means that, well, there must be a y value in the range such that there's an x value in the domain. And this is how we define the inverse. So in order to go back from the range to the domain, we use the inverse function. So we are able to go back and forth as long as the functions are one-to-one. So to get to the domain and range, we use f, and to get back from the range to the domain, we use the inverse function. Okay. So some facts that are apparent. When you use an inverse, remember that your x and y's in your domain and range will swap. They will flip over. So if we are using the inverse, this means that the domain of f becomes the range of the inverse function, which is right here. And the range of the original function now becomes the domain of the inverse function. So when we do inverses, domain and range, x and y's switch places. Okay. And to verify that two functions are inverses of each other, that if we compose them, we should always arrive back at x. So this means that if we started at x and use function f, we would get to y, but then if we use the inverse, we should always arrive back at x. Or you can even do the other way. You can say f composed with the inverse, so you can go x to y again, and you can use the original function to get you back to x. So basically, the functions undo each other. So if you have true inverses of each other, you should always arrive at x. All right. All right. So that means that when you compose, so if you guys remember compositions, when we compose functions, remember that you take the domain of the inside function. So when we say the inverse composed with f of x, you should arrive at x if you have true inverses. And if this is the case, then the inverse now takes the domain of f. And then if you go the other way, if you do the original function composed with the inverse, and if they're true inverses of each other, you will arrive at x. But this time, the original function will now take the domain of the inverse function. Whew. All right. So again, this is stuff we all should know already. Which brings us to 3. Verify that the inverse of x cubed is the cube root of x. So the only way to verify that these are inverses is to compose them with each other. So we'll do this one way. So we'll say 1. We're going to say g composed with the inverse of g of x gives me g of the inverse g of x. Now, what we do here is we notice that the inverse of g of x is the cube root of x. So that's what we're going to plug in to function g for every x. So we're going to take the cube root of x and plug it in for x into function g. So this means that you will get the cube root of x cubed, and the cube root and the cubed power will cancel and leave me with what?
X.
X. So does this prove that they are true inverses of each other?
Yes.
Yes. Good. And of course, we can check it going the other way. 2. I can say g inverse composed with g of x will give me inverse g of g of x. Now remember that g of x is x cubed. So we'll get g inverse of x cubed, and now plug it in for x into the inverse function g. So you'll get the cube root of x cubed, and again, the cube root and the power of 3 will cancel and again leave us with x. So we see that no matter which way we compose, we still arrive at x. So therefore, these two functions are definitely true inverses of each other. Okay. Any questions on that?
Nope.
All right. Nothing new, right? Okay. And then if we are told to graph inverses, well, remember that inverses are symmetric to the line y equal, or symmetric with respect to the line y equals 8x. So here's my line, y equals x. And if you have true inverses, then their graphs reflect across this line. So you would have a point A, and over here it would reflect and give you A prime. Here you'd have a point B prime, and it could reflect and give you the point B. So these points are symmetric across this line. So that's how your inverses work. Okay, so that's graphically. All right, let's keep going. Next, we are going to find the inverse of an equation. So remember, there's a couple steps to doing so. So the first step is to take the function and replace f of x with y. So I might as well just walk through these steps while we work the next example. Okay, so here we want to find the inverse of f of x equals x cubed minus 1. So the first step is to rewrite it as y equals x cubed minus 1. And now the second step is to interchange the roles of x and y. So remember, if this function's 1-to-1, then it will have an inverse. And if you have an inverse, remember that your domain and range switch places, and your x and y values will switch places. So on step 2, you're going to interchange the roles of x and y, and this will give you x equals y cubed minus 1. So we interchange their roles. And now, step 3, all we have to do is solve for y. So step 3, you'll move that 1 over and you'll get x plus 1 equal to y cubed. And then to solve for y, what would you do to both sides?
Square root. Cube root it.
Cube root, good. You would cube root both sides. And we would end up with the cube root of x plus 1 equal to y. Okay. And then step 4, we have found the inverse. So write it as the actual inverse. Okay. So there's the inverse. But now we want to graph both functions. So let's go ahead and graph x cubed minus 1 first. So to do that, I'll just create a little XY chart. X and y equals x cubed minus 1. All right. Okay, so what are some common points to pick when graphing any function?
0.
29.
0. What was the other one? Did you say 29?
No.
Let's go 102.
Sounds great. How about we just choose -2, -1, 0, 1, 2. The most common x values to choose when graphing a function, right? Okay,
That's
now
pretty
take these x values and plug them into for that x. So if you plug in -2, -2 cubed is -8. And -8 minus 1 gives me -9. And then if you plug in -1, -1 cubed is -1, and -1 minus 1 gives me -2. Plug in 0, you get -1. Plug in 1, you get 0. And then plug in 2, you get 7. So let's go ahead and plot that first. Okay. So fun colors, let's see. There we go. -2, -9, which is right there. -1, -2, 0, -1, 1, 0, and 2, 7. Right there. Here is what f of x looks like. I'll do it in blue. Come on, graph for me. Okay, so here's f of x. Okay, so now let's go ahead and graph the inverse function. So x and y equals the cube root of x plus 1. Do we have to pick new numbers?
No.
No. All we have to do is take these values and do what with them?
Cube root them.
I mean, we could, but what did I say with inverse and original functions? Your x and y's will,
You flip them, right?
Same.
you flip them. So this would be -9, -2, -2, -1, -1, 0, 0, 1, and 7, 2. So if you have the values for the original function, all you have to do is flip them. Okay, which means let's go ahead and graph that one. -9, -2, -2, -1, -1, 0, 0, 1, 7, 10, 9, 8, 7, and 2. And here is our inverse function. Come on, graph. There we go. And there's the inverse function. Okay. Now, remember, if they are inverses, then they should be able to reflect across the line y equals x. So here's my line, y equals x. Do these graphs look symmetric across this line?
Yeah.
Good. This point is 7, 2. If I reflect it over that line, then you get this point, which is 2, 7. All right. And I guess there's one more thing we could do here is do the domain and range. So the domain of f, or the domain of x cubed, and even x cubed minus 1, is all real numbers. And the range of f, well, that's also going to be all real numbers. Which means if you were to find the domain and range of the inverse, well, this one's kind of too easy. All you would do is take the domain and range of the original function and swap them. But since they're the same, you're gonna get the exact same values for your domain and range, which is reflected on the graph to the right. Okay, and that's how you find an inverse. Of course, we could definitely check our work to make sure they are true inverses of each other. So we can always check by composing. We could say G compose with the inverse of G, which would give me G of G inverse of X. This would give me G of the inverse function, cube root X plus 1, which would then be plugged into the original function for X. Well, I used G, I should have used F. Either way, which means that we would get the cube root of X plus 1 minus 1. Oh, that should be to the third. And again, the cube root and the cube power would cancel, leaving me with X plus 1 minus 1. And what would we be left with?
X.
X.
Just X. There we go. Which means, yes, these are definite inverses of each other. I mean, we put the work in there, the graph proves it, but again, you can check graphically and you can also check algebraically. All right. Any questions on that page? No, all good then?
Yep.
All right. Which means go have some fun. All we want to do here is just find the inverses and check the results. Okay. So Here we're given f of x equals 2x plus 1 over x minus 1. So remember, to find the inverse, we have a couple steps. Step 1, go ahead and rewrite it as y equals 2x plus 1 over x minus 1. And then step 2, interchange the roles of x and y, which means we get x equals 2y plus 1 over y minus 1. So we interchange on this step. Okay, and then step 3 is solve for y. All right, so looking at the above setup, we want to solve for y, but y is in the denominator. That means I have to take this y minus 1 and multiply it to what side?
The other side.
The other side. Good. So you'll get x times y minus 1 equal to 2y plus 1. So all we did was multiply that to the left side. Okay, and now we have to solve for y. So what's our next step?
Can distribute it.
Distribute. Good. You get x times y minus x equal 2y plus 1. And now again, remember that you're solving for y. So you want to put your y's together. So you're going to move 2y over to the left side. So x minus 2y equal to, and you'll move that x by itself over to the right side. So x plus 1 or 1 plus x, whichever you like. All right. And now remember again that you're solving for y. So what are you going to do on the left side?
Factor out the y, divide everything.
Divide x minus 2 to the other side.
Good. Factor out a y and then divide by x minus 2. And y equals x plus 1 over x minus 2. And now we have found the inverse, so we write it as the inverse. So for f inverse of x is equal to x plus 1 over x minus 2. There's the inverse. Oh, but now the fun begins, because we're going to check our work. All right, but before we do, any questions on that process? All right, so let's check. We're going to do f composed with the inverse. Yeehaw. Which means that we get f of the inverse of x, which means we get f of our new inverse, x plus 1 over x minus 2. Now remember, all of this is going to be plugged in for every x into the original function. So we get 2 times x plus 1 over x minus 2 plus 1 over x plus 1 over x minus 2 minus 1. And now simplify. Okay. So this becomes 2 times x plus 1 over x minus 2 plus 1. And I'm going to make this into a fraction, put it as 1 over 1. So let's just look at the numerator for now. If we want to combine these two terms together, we need to multiply by a common denominator of what?
X minus 2.
Good. Now, let's look at the denominator. You have x plus 1 over x minus 2 minus 1. Put that over 1. And do we multiply by the same denominator?
Absolutely.
Yes.
Absolutely. Yeehaw. Now we're on our way. And now we get 2 times x plus 1 plus x minus 2 over the same denominator of x minus 2 over x plus 1 minus x minus 2 over the same denominator. Oh, doesn't this bring back great memories?
No.
I'm a second that.
Did the X minus 2's cancel out?
They will when we multiply by the what?
Reciprocal.
All right, but let's not do that yet. Let's go ahead and fix the numerators of the numerator and the denominator. So here, we'll make it this simple, right? That becomes 2x plus 2 plus x minus 2. So what's going to cancel?
Twos.
The
Yes.
2's. So you get 2 over x minus 2. Sorry, not 2. You get 3x over that over. And then if we simplify this, that's x plus 1 minus x plus 2. And who's going to cancel there?
Your X's.
This.
And you get 3 over x minus 2. Now that looks a lot easier. So you multiply by the reciprocal. And what cancels?
X minus 2's.
X minus 2.
X minus 2's, and what else?
The 3's.
The 3. What are we left with?
X.
Oh my goodness. Are they true inverses of each other?
Sure.
Absolutely.
I only got one question.
Yo, what's up?
Remember when you said this is when the fun begins? Where's the fun?
You didn't see that as fun?
That was beautiful, man.
Okay, give that to a
Right.
4th grader and they'll solve that. All right. The algebra, man. Gotta love the algebra. If you hate algebra, calculus is gonna be terrible for you.
No, it's just a joke. It's actually not bad.
I know. I know.
It's T's.
I know. All right, one more. Let's do it. Well, there's more, but this is the last one here. All right. Step 1, y equals 2x over 3x minus 1. Step 2, interchange. X equals 2y over 3y minus 1. Step 3, solve. And that means I'll just multiply the denominator to the left side. And you'll get x times 3y minus 1 equal to 2y. And what do we do on this step?
Distribute.
Distribute 3xy minus x equal to 2y. What are we solving for?
Why?
I.
Y. Put your y's together. Bring that 2y over. Move that x over. And now what are we going to do on the left side?
Factor it out.
Factor out and divide.
Factor out the y and then divide. So y equals x over 3x minus 2. There you go. You found the inverse. So write it as such. And the inverse is x over 3x minus 2. And do we believe in our work or do we want to check this?
I believe it in work. You don't
Yeah,
have-
we good.
My
We're
faith
good?
is strong in this one.
We believe. Perfect. All right. Any questions on this page?
But you said just in case we wanted to check it, we just replace x with the inverse.
I was just joking with the we
Is-
believe.
You go
Is
ahead and
there
check it
a-
then, Luis.
Is there a certain name for when the inverses are like the same thing, like the original function itself?
Like when the inverse is the inverse itself? Or
Yeah, because I remember
like
last
it
year on a
doesn't
test it
change?
had one of those. Yeah, something like that.
Yeah, unfortunately, there's no cool name for it or anything. Just knowing that the original function is its own inverse. But yes, to that first question that was asked, if you wanted to check your work, then yes, you can compose. So you would take this, and plug it in for every x and do everything we did up there.
I checked it. It's good.
Perfect. You came out with x. All right.
No, you're kidding. Yeah, I did.
All right. We're good with that. Okay, cool. So that's the process to finding inverses, which is gonna be the same process when we deal with the trig functions. Okay, just no fractions involved. A lot of compositions. All right, now we are on the last one for today. Now this one's important because remember that x squared that we saw on the first page. So remember that x squared is not a one-to-one function because if we draw a horizontal line through it, we intersect it twice. But what's great about math is that we can restrict a function's domain to make it into a one-to-one function. So for this function that we're given, x squared plus 1, we are going to restrict its domain to all x values greater than or equal to 0. Okay, so let's go ahead, since we restricted to that, let's go ahead and graph it first to see what it looks like, to make sure it's actually one-to-one. All right, I'll put that XY chart right here. Okay, so for the first one, x and y equals x squared plus 1. We're restricting the domain to anything greater than 0. So remember, the domain tells you what numbers to pick. So what number should I start with?
1.
0.
0.
Oh, true.
And then 1, and then 2, and then 3. I think that's all that's going to fit on our graph. So if I plug these x values into that function, well, 0 plus 1, you get 1. 1 squared plus 1, you get 2. 2 squared plus 1, you get 5. And 3 squared plus 1, you get 10. So I'm going to go ahead and graph that already. So 0, 1 right there. 1, 2, 2, 5, and 3, 10. So here is our domain restricted x squared plus 1. Come on. Now, if I draw a horizontal line through it, I only intersected how many times?
One time.
Ah,
Which means, is it a one-to-one function?
Absolutely.
Which means if it's one-to-one, we can find its what?
Inverse.
It's
inverse.
inverse. Good. All right. But before moving on, we can already get the domain and the range. And the domain's given to us, x greater than or equal to 0, or 0 to infinity. What would the range of this function be?
1 to infinity.
1 to infinity. We can say y greater than or equal to 1, or 1 to infinity. Okay, so that'll set us up nicely when we come to the graph of the inverse. So let's go ahead and find the inverse now. So run through those steps, right? Let's do that here. So step 1, we make it y equals x squared plus 1. Step 2, interchange. X equals y squared plus 1. Step 3, solve. So move that 1 over, and x minus 1 equals y squared. And then do what to both sides?
Square it.
Root.
Square
I mean,
root it.
root it. Root it. Sorry.
And you'll get plus or minus the square root of x minus 1 equal to y. Now, which one do we keep? The plus or the minus?
The plus, right? Because the y or the range would be, or
Positive.
no, the domain would be y is greater than or equal to 0. No,
So
wait.
if you thought about it, right? Because you know you're going to swap these, right? So that means your domain is going to be anything greater than or equal to 1 once we swap them, which means if you're greater than 1, are you positive or negative?
You're positive.
Positive.
You're positive. So we take the positive one. All right. So that means 4, we get f inverse of x equal to the square root of x minus 1, the positive one. There's our inverse. Okay, which means we can move on to graphing it. And I have x and y equals the square root of x minus 1. Do I have to pick new numbers?
No.
No.
No, we take these and
Flip it.
flip it. 1, 0, 2, 1, 5, 2, 10, 3. Now let's
Are you ever
plot.
gonna have to pick new numbers?
We shouldn't have to, but it could depend on the domain, but we should never have to. I've never had that issue, but it could come up. 1, 0, 2, 1, 5, 2, 10, 3. Here's our inverse function. And then here's that line, y equals x. Do these look symmetric other than my drawings?
Yes.
Yeah.
Well,
The points do.
Good. So this would be, what is this? 2, 5. And reflected across, that would be 5, 2. Okay, which means that the last piece we need is the domain and range, which means you take the domains of the original one and flip them. So what's my domain going to be now?
x is greater than or equal to 1.
And what's my range?
Y is greater than or equal to 0.
There you go. Okay. And there it is. The biggest takeaway from this problem, though, is that we can restrict any function's domain to become one-to-one. So that's going to be very important on trig functions in the next section, because remember that sine looks like this. And if you drew a horizontal line through it, you would intersect it an infinite amount of times. So is sine a one-to-one function?
Not currently.
Negative.
No,
No. So in the next section on Tuesday, we're going to learn the proper restrictions to make cosine and sine one-to-one functions. And I think tangent. Yeah. And then after that, it's the inverse. So that's what this is preparing you for. We are given the power to restrict the domain's function to make it a one-to-one. So if it's not one-to-one, we make it one-to-one and we make it have an inverse. So that is it for today, y'all. Those are inverses. So if you got questions, stick around. If not, see you on Tuesday.
I was gonna ask, did you